Hello, good evening everyone. Welcome to the course of Foundations of Cryptography live session. So this is week 4 of the live session and I will be discussing the topics of the lectures that are given for week 4 on the NPTEL website. For the assignments of week 4, the submission deadline is I think 20th February. So this week I will just discuss the questions regarding week 4 lectures. And next week again we will discuss week 4's assignments questions. Along with that, I will also discuss the week 5 topics in the next week. Okay. So let me share my screen and is my screen visible?
Yes, ma'am.
Okay. Thank you. So these are the topics for this week. CPA secure encryption from PRF, that is pseudo-random function, modes of operation of block ciphers, theoretical constructions of block ciphers, and practical constructions of block ciphers. So let's start. First question is written here. Consider the following keyed function f. For security parameter n, the key is an n cross n Boolean matrix A and an n-bit Boolean vector B. Define f with key A, B that maps n-bit length input strings to n-bit length output strings by the function defined as fab of x equal to ax plus ab, where all operations are done modulo 2. Show that f is not a pseudo-random function. So it is already mentioned in the question itself that f will not be a pseudo-random function. You just have to prove it. Okay. So I will wait for your response for maybe 1 minute. You can write it in the chat. What will be the idea? Why do you think that this particular function defined in this way, ax plus b? So you can see here, A is a Boolean matrix of dimension n cross n. So A is a square matrix. You are multiplying this matrix with x. So x is the input that comes from this space, that is n-bit length input space. So x is also a n-bit length binary vector. So you are multiplying this Boolean matrix of dimension n cross n with x, which is a Boolean vector of dimension n. And so the result of matrix vector multiplication will be again an n-bit or n-dimensional binary vector. And you are adding another n-dimensional binary vector b with this. Both A and B are secret in the view of the adversary. But still, we will claim that f will not be a secure pseudo-random function. So why is that? Or maybe you can state some strategy by which you can know the values of A and B. The secret value will be leaked. But how? How you can exploit the security game of a pseudo-random function to find the values of the underlying secret A and B for the function f. So I will wait for some time for your response. If you remember the security game of PRF, how does that work? So as usual, okay, there is a response in the chat. For x equal to 0, f will be b. Great, very nice, Viresh. So b will be leaked that way, right? And then a also can be leaked, right? Right. So once b is known, you will get to see basically the values of a dot xi for several xi's, and you can retrieve a from that. That is simply solving the linear equations, right? So let me just explain it formally how in terms of game you can retrieve the value of A and B. So there is this uh, challenger of the PRF game, and there is this adversary. And how the PRF game, security game works. So adversary is allowed to query for any inputs of its choice. So adversary can query with X size. Of course, they belong to n bit length binary vector, right? So any xi adversary can choose, and it will get to see the value of f a comma b of xi, and it can repeat polynomial number of queries in this manner. And then finally adversary has to, so of course the challenger either chooses to respond with the PRF value on input xi or a truly random value on the input xi. So there will be no key, it will be a truly random string of bit n of dimension n, right? Any one of them, that decision is made in the very beginning of the game by the challenger, right? So let's say if b is 0, so challenger chooses a bit b. It is just the security game of PRF. Challenger at the very beginning of the game chooses a bit b among 0 and 1. If b is 0, challenger will always send, let's say, value of PRF evaluation on the query inputs. And if b is 1, then it will always choose a truly random value on input xi to send to adversary. And once this query phase is over, adversary is expected to respond with a bit b dash, saying that whether it was interacting with a PRF challenger or a truly random function challenger. Okay, this is the PRF game. Now, how the adversary can exploit, as Viresh already answered. So the game you can craft it in this manner, that first adversary will query. So adversary is free to choose its own query input, right? So it will choose first x to be all zero string, right? And then if the challenger is actually responding with a pseudo-random value, then it will get to see actually a dot all zero, right? So a dot x, this part will be 0, and it will get to see the value of b exactly. Okay, so and then again it can query with x2 in this form. Let's say x2 will be some, let's say 0, and then ith bit as 1, and then rest of the bits again 0. So out of n binary bits of the input, ith bit we have put it as 1. So what will happen then if the response is coming from a PRF? It will return basically the ith column as the response, right? B is already known, remember. So basically whatever it has seen, so for a, uh, so A is a matrix, right? Let's say it has this form A11, A12 till A1n, A21, A22 till A2n, and then A1, AN2 till ANN. Now, if you multiply this with a vector of this form, right? So 0, 0, 0 for till I minus 1 row, and then a 1, and then again rest of the elements 0. So if this is the form, then what will you get in the result of, so this is a dot xi, I am saying. So what will you get? This will get you the ith element, all the elements of ith column, right? So this element will be coming. So A1i, A2i, all of them will be known. So the ith column is retrieved. So if you query like this n times with making the ith bit 1 for each of the ith query, Okay, so first query is of the form 1 all 0. Then you take the query as 0 1, then all 0. Then you take 0 0 1 all 0. Like this, you do like this n times query, and eventually you are able to retrieve all the columns of A. So that is the whole matrix A is retrieved, and also B is already known, right? So like this, you can retrieve the value of, so basically what we are trying to show here is that the output of f a b comma x is not pseudo-random, or is not indistinguishable from a random string, random vector of dimension n. By seeing several evaluation of f a b comma a comma b over x with x of the choice of adversary, it can actually distinguish the output of pseudo-random function from a truly random function. Hope this is clear. Okay. Okay. So let me proceed to the next question. So the question says that prove that if f is a length preserving pseudo-random function, then g of s defined as f of s on the input of 1 concatenated with fs on the input of 2. Like that, you continue till evaluating fs. Okay, there is, ma'am, please repeat once. You mean to say the previous question, question 1? Kunj? Okay, okay. So, okay, I am going back. So, can you just unmute yourself and let me know what your exact doubt is and at which point you were unable to understand? That will be easier for me to explain.
Yes, ma'am.
Yes. So, where exactly?
मैम
Yes.
मैम
Yes.
मैं थोड़ा लेट ज्वाइन हुआ तो क्या आप पहले से रिपीट कर सकते हो, थोड़ा
Okay.
एक्सप्लेन कर सकते हो?
Okay. Okay. I will do that. Sure. So the question, is it clear
ओके
to you? Was the question is clear to you? You are given a function, okay, that has two key, A and B. A is a n cross n Boolean matrix, and B is a n-dimensional Boolean vector. Both of them are serving as key to this function. F is a keyed function, and A and B are the key of that function. And your input is a n-dimensional Boolean vector. And the way you evaluate this function is this. F of x for the key a comma b is defined as ax plus b. Ax is a matrix vector multiplication, and with that you are adding one more n-dimensional Boolean vector. So final output is again your n-dimensional Boolean vector. The function definition is correct, right? Clear? Is the function definition clear? Okay. Now I have to prove that f is not a pseudo-random function. So what is the meaning of pseudo-random function? Basically, if you are dealing with a truly random function, then what happens is that or for any input, right? So all the okay. So the very definition of the very basic concept of pseudo-random function is what? That you see xi, xj for these inputs. If you see the evaluation of these inputs, okay, for input xi, your value of PRF is f of xi with key k. For input xj, your value of PRF is f of xj with input k. Now, even if xi and xj can have some relation between them, even if they are correlated, you cannot find a defined correlation between the output of the PRF. Because if it would have been a truly random function, okay, if it would have been a truly random function, then how your truly random function generates output for some input? You give some input to truly random function and it basically samples a uniform random string from the output space. Okay, that is how your truly random function works, and return yi as the output of this table. So in truly random function, you store all the, let's say, all the input with n bit length, right? Here both the input and output space has bit length n. How truly random function outputs? You choose some arbitrary xi, okay, some n bit length string, that is your input. It will just sample some random value of dimension n, okay, binary value, and that it will assign as the output. Okay, so yi has really nothing to do with the input xi. It does not at all use the value of xi to find the value of yi. So although this is a function, I am saying for input xi the value is yi. In case of truly random function, yi has literally no relation with xi. And then again, you query with some other xj, okay, in the input, and it will again sample uniformly randomly from the output space another yj, okay, and populate the table. So like that, you can think of truly random function. So all the output has nothing to do with the corresponding input. And that is why even if xi and xj has some relation in between them, although if it is there, let's say it can be the case that xi is complement of xj, okay, bitwise complement. Even if in that case, you will find no relation literally between yi and yj, because both of them are independently sampled from the output space and has nothing to do with its corresponding input. That is the concept of truly random function. But when we deal with pseudo-random function, then our key is secret, right? So key is not known to adversary, but then we define some functionality with this key k and input x. So it actually uses both the value of input and the value of key to generate some output, let's say yi dash or xi. And our target is that although yi dash uses the value of xi in the computation of this function, but still we will able to achieve this scenario that for some other xj having some correlation with this input xi, its corresponding yj dash, that is the prf output for xj, will have nothing to do this prf output of yi dash. Okay, so the output will still be indistinguishable from a truly random output. Okay, so it will look like random, but it is not actually random. Okay, now in this particular function, we can easily see that for choosing some specific query like this I have shown here. So if you query the prf oracle with the value of all zero string, what you get in the response is the value of b itself. So a part of the secret is already leaked. That is where only you can claim that this is not pseudo-random, because part of the secret is leaked. Not only that, you can even show that A can also be leaked with particular query input you can choose. Okay. So if you choose X in this manner, let's say if you choose the first bit to be 1 and rest n minus 1 bit to be 0, then A dot X will actually give you back the first column of the secret matrix A. Again, part of the secret information is leaked. And if you continue like this n times query by fixing each of the ith bit of input X one after another and keeping the rest of the n minus 1 bits 0, you will eventually learn all the columns of the matrix A. So the whole secret, the matrix A and the vector B is leaked. And if that is the case, you cannot anymore claim the security of the function f, because you can clearly distinguish this value from a uniform random value that is chosen from the n bit length space. Okay. Does that make sense, Kunj? Why this is not secure?
Sorry, ma'am, I don't know.
Okay, I think have you gone through the concept of PRA, or have you watched the lectures, the initial basic lectures on the website?
Yes, ma'am. Yes, ma'am. But I don't able to understand more.
What you don't
I
able to
just
understand? Huh?
just watch more than fight and bus, but I don't understand.
Okay, what exactly, can you tell me what exactly is the problem? Like, is the definition of pseudorandom
Um,
function clear to you?
yes, ma'am. But
Hmm?
some probability for mathematics or metrics, I don't know because I am from commerce background.
Okay, so you are not able to understand why, like how a dot x this particular computation is going on?
Yes, yes, ma'am.
Okay, so that is okay. I understand. So basically, that has nothing to do with this particular question. This is the basic linear algebra mathematics knowledge. So I would suggest, so this recording will be provided to you later. Okay, I would suggest you try to find some basic linear algebra mathematics. It is really not nothing difficult. Okay, so it is just you even in maybe you just search in your browser the matrix vector multiplication, how is it done. So they are nothing but some integers that I denote with, so there are n rows, n columns, each element is, you can think of this 0 or 1 element. And how the computation is done, the matrix vector multiplication, you simply search your browser and you will get to know how matrix vector multiplication works. Okay, I think that is
Okay,
what you
ma'am.
should look
Thank you.
into. It has nothing to do with this particular
Okay,
question. Okay. And then you come back and watch the
okay, okay.
lecture. I think that will be clear. But
Okay, ma'am. Thank
thanks
you.
for asking. Huh? Okay. Okay. So this question, so I think it was already discussed in the lecture that how you can generate pseudorandom generator from pseudorandom function, right? So pseudorandom, uh, so you are given a secure pseudorandom function f, which is length preserving. What does that mean? Length preserving means your input and output length will be same. Okay. So if your input has bit length n, your output also has bit length n. So you can also say that this is a PRP. Okay. So that is okay. So f is given as a secure PRF. Now you are trying to construct a PRG where S is the seed and you define in this manner. Okay. This is concatenation. So f of 1 with the secret S, that output is simply concatenated or appended with f of 2 with key S. Like that is, it goes on till L times. Okay. 1, 2, 3 till L. And every time you evaluate the pseudorandom function f with the secret S. And this is also given that uh, this G will be a secure PRG, but you have to prove formally. This is a very generic way to generate PRG from PRF, and there is also method to generate PRF from PRG. But anyway, let's focus on this. Ma'am, how do we know it is a PRP? Well, so okay, maybe okay, this cannot be okay. So thanks for pointing it out. So it may not be PRP, may not be PRP. So I am wrong to say that it will be a PRP, maybe, because in PRP there has to be a defined inverse function as well. Okay. So not only the input and output length are same, but also there must be the invert function well defined. But yes, so it's just given as length preserving pseudorandom. So thanks, Viresh. May not be PRP. So input and output length same. That is a criteria for pseudorandom permutation. but here it is just said that it is a PRF, but length preserving. Okay. Now, what is expansion factor? So if your seed has input length n bit, then because it is already given that this is a length preserving PRF, so f of 1 with, so this output has bit length n, this output also has bit length n, and till L times it will be continued. So in total, ln number of bits are there in the output. So your PRG input length is n, then output length is ln, and that's why expansion factor will be ln. So this part is clear from the way it is defined, that it will be true, but whether it will be a secure PRG or not, that you have to prove formally. So anyone would like to answer that how I can prove that? Maybe you can suggest me the game. So you already know, right, that to prove a system secure, we generally base the security of that construction on some other well-established construction. So here it is given that F is secure. Now I have to show that we first assume that G is not secure, and then we show that this will imply that F is not secure, but it is already given that F is secure. So by contradiction, we will declare that G is secure. That is what is the general technique for proving that some system is secure. So we will base security of our PRG upon the security of PRF. So anyone would like to volunteer to write the game? So let me just structure it. Maybe there is this adversary A2 who is able to distinguish the output of PRG-G from truly random output. So AD2 is able to break the security of G, and assuming that, I want to show that then AD1 will be able to break the security of PRF-F while playing the game with challenger CH. So anyone would like to volunteer to tell me what will be the communication between them, challenger AD1 and AD2. AD2 breaks security of G, and AD1 is expected to break security of PRA. So how will this happen? Anyone?
Ma'am, first the challenger will send Y to the adversary 1.
Challenger will, sorry, repeat again. Challenger will
send the Y that can be G of S or that can be random depending on the value of B. So ma'am, we can just assume if B is equal to 0, then Y is equal to random R, and if B is equal to 1, then Y is equal to G of S.
okay. So you are saying that will be done by challenger CH, or maybe because I can just give you a hint that between AD1 and AD2, the security game of PRG is going on. What you are saying is the game of PRG, right? And between this challenger CH and AD1, the security game of PRF-F is going on. Now, yes, you are true that adversary 1 is supposed to send either a truly random output or a output of this PRG to the adversary AD2, right? You were on the correct track.
Yes,
You
ma'am.
can just little bit
Yes, ma'am.
rearrange. Yes.
Yes, ma'am. In that case, adversary 1 will first send input to the challenger, and then the
Right.
challenger will, yes, ma'am.
Right. Very nice. Who was answering, by the way? What's your name?
Biresh Kumar Singh.
Okay, Biresh. Okay, thank you. Yes, you are correct. So what AD1 does is it is playing the game of PRF. So as usual, challenger will decide either it will send the PRF output or truly random output. Okay. Now whatever it decides, depending on that, it will always answer the query in the same manner. So adversary queries with the input 1 first. In response, it will see yi, which can either be the PRF evaluation or truly random evaluation. Query with 2, cy2, y1, y2, so on. Query with L, cyl. Now it has gathered all the value y1 to yl. Okay, it concatenates all of them and sends to adversary 2. Now, from the view of this adversary AD2, what happens is that if challenger chose to send out the PRF value in the form of yi's, then this is nothing but the output of PRGG. And if challenger had chosen to send out TRF value in the form of yi, then all these L strings, y1, y2, all of them are truly random strings. So this will be a value of truly random string. Okay, truly random string in the view of adversary AD2. And because we have assumed that AD2 is able to break the security of G, then it will successfully return some B dash, denoting that whether it is interacting with a pseudo random generator or truly random generator. And AD1 just directly forwards that same bit B, and see that with exact same probability with which AD2 is able to break the system, AD1 will, AD2 is able to break the system of PRG, with the same probability AD1 will be able to break the system of PRF. And so if AD2 exists with non-negligible, AD2 exists such that it is able to break the security of PRG with non-negligible probability, then AD1 will also be able to break the security of PRF with non-negligible probability. But we know F is already secure, so there cannot be any PPT adversary existing who is able to break the security of PRF with non-negligible probability. So that is a contradiction, and hence we say that AD2 cannot exist. So PRG is secure. That's how we say that PRG is secure. Is it clear? Also, let me mention that I think 5 minutes left to this particular Zoom meeting will end, and then take a 10 minutes of break, and please join again. Okay. After 10 minutes, I will open the same Zoom link. Okay. So is this answer clear? And I will then proceed to the next question. So here is the next question. Let f be a pseudo-random function, and okay, someone is saying yes, ma'am. Okay. Thank you. Okay. Let f be a pseudo-random function and g be a pseudo-random generator with expansion factor L of n equal to n plus 1. For each of the following encryption schemes, state whether the scheme has indistinguishable encryptions in the presence of an eavesdropper and whether it is CPA secure. So there are 3 cases. Again, expansion factor means that if your PRG has seed length of n bits, then the PRG output has length n plus 1 bits. Okay. So there are pseudo-random function f and pseudo-random generator g. Now there are 3 encryption scheme defined. For each of them, you have to say whether it is secure in presence of eavesdropper. Indistinguishable encryption, you remember, right? When do we say that indistinguishable encryption? In presence of eavesdropper and in presence of a CPA adversary, chosen plain text attack adversary. So let us take one after another. So to encrypt M, here message is of bit length n plus 1. How do you encrypt? You choose a uniform R, that is n bit length random string, and then output the ciphertext R, G of R XORed with M. So R is random for every message, and then you send G of R XORed with M. So is this, first let me know in the chat whether do you think this encryption is indistinguishable in presence of eavesdropper? Indistinguishable encryption in presence of eavesdropper means that the adversary is able to see ciphertext of either M0 or M1, and it has to determine whether it is seeing encryption of M0 or M1 by looking at the ciphertext. Yes, ma'am, R is random. Okay, Videsh, your answer is not correct actually. So let me tell you why. Just say that yes, R is random, but R is a part of the ciphertext. See, R is random, right? Every time you encrypt a new message M, you take a uniformly random R, but R is given as part of the ciphertext. Now what happens is that you know already R, right? That is the seed of the PRG. And the PRG algorithm is public. So G of R, you can yourself compute once you have the knowledge of R, right? Then you just take the first part of the ciphertext, which is R. You run the PRG algorithm on your own with by using R as its seed, and then you XOR the value with the second part of the ciphertext, which is already as this form. Now this ZR XORed with ZR gets cancelled, and what you are left with is the actual message M. So you with probability 1 can retrieve the message M, right? So it is not secure in presence of eavesdropper. That is the minimal security requirement. That is the least powerful adversary. But even in presence of least powerful adversary, this encryption scheme breaks. It would have been secure if R would have been secret, right? Then you just return Z of R XORed with M as the ciphertext. Then it is secure in presence of eavesdropper, but it will not be secure in presence of CPA adversary because it is a deterministic encryption scheme that we discussed earlier also. But for being secure in presence of eavesdropper, R has to be kept secret. But here you are sending R itself as the part of ciphertext, right? That's why it is not secure in presence of eavesdropper. Is it clear, Viresh? And others also? Okay, so is it clear that why the first one is not having indistinguishable encryption in presence of eavesdropper? Is it clear?
Yes, ma'am.
Okay, thank you. So again, if it is not secure in presence of eavesdropper, then it is also not secure in presence of a CPA adversary. Because as we already said that a CPA security, in case of CPA security, the adversary is given more power than in case of eavesdropper. So even like if a less powerful adversary is already able to break the system, then of course a stronger adversary will or must break the system, right? So if it is not secure against eavesdropper, then it will not be secure against CPA adversary also. So the first one is not secure in both the cases. Now coming to the second one. So here the encryption scheme is defined as for encrypting a n-bit message, the ciphertext is M XORed with FK so encryption is defined as M XORed with f of 0 to the power n for an unknown key k. So of course k is the secret of PRF, but the PRF is always evaluated with this value, a fixed x value, right? 0 to the power n is fixed always for any message n. Now, what do you think about its security or about whether it satisfies the indistinguishable encryption in presence of eavesdropper? Then we will see the CPA security part. First, answer about the eavesdropper part, whether it is secured in presence of eavesdropper. I am not audible. Kapil, so am I audible to others? Just confirm. Hello. Okay. So Kapil, you
Yes,
can
ma'am,
just
you are audible.
okay. Then Kapil, you can just join 1 second. So rejoin. Okay, so let me proceed. Yes, so coming back to the question, what do you think about the security in presence of eavesdropper? Anyone? Let's say what is indistinguishable encryption. Let's say we have two messages M0 and M1, and the challenger is encrypting any one of them and giving you the ciphertext in form of MB XORed with FK 0 to the power n. K is not known. So are you able to know what B is there, whether M0 is encrypted or M1 is encrypted?
No, ma'am.
Yes. I did not get your answer. Said anything? Is it secure?
Ma'am, it will be secure. Yes, ma'am. I think it is secure.
Right. So it will be secure. Your answer is correct. Why? Because since K is secret and F is a pseudo-random function, so for any input, although I always use this fixed input 0 to the power n, so you are seeing just one ciphertext in case of eavesdropper. So you are seeing this, and although by the encryption algorithm defined, you know that this part is going to be the PRF evaluation on this particular input, but you are never able to distinguish or guess the exact value of the PRF evaluation on this input, right? Because it is a pseudo-random function. Although you know the input, you can't guess the output, what is actually going to be. So now this you can consider as XORing the message with a pseudo-random string. Like this, I was saying in the previous case, I said that if you are XORing M with output of PRG with the seed secret, then it is secure against eavesdropper. The same thing applies here. Here also you are XORing the message M with a pseudo-random string. Why it is pseudo-random? Although the input 0 to the power n is known, the K is secret. So output of the PRF is pseudo-random. So XORing the message M with a pseudo-random string will give you back the ciphertext. So you don't know with what exact pseudo-random string your message was XORed. So you cannot guess whether it was M0 or M1. Okay. That is why it is indeed secure against eavesdropper. But what about CPA security? Any comment on that? Will it be CPA secure? Anyone? Think of whether it is a deterministic or randomized encryption scheme. Is it a deterministic encryption scheme?
Yes, ma'am.
It is deterministic. So will it be CPA secure? Well, so if you remember, for CPA security and for a stateless encryption scheme, it is a required condition that the encryption must be randomized. Deterministic stateless encryption scheme is never CPA secure. So what stateless is, that will come later in this week's video only, in this week's discussion only. But for now, let's see that every time you for now, if you are encrypting M1 with XORing M1 with FK 0 to the power n, next time if you are encrypting M2, you are using the same pseudo-random string to XOR with M2, right? So this part is always same, right?
Yes.
So that is why
Yes, ma'am.
it will leak some information about the underlying message, right? This is a deterministic encryption scheme, and in CPA security, you are allowed, or the adversary is allowed, to query the encryption oracle with messages of its choice or plain text of its choice. So it can exploit the encryption oracle to guess the how or what is the underlying message of the challenge ciphertext CP. So it is not CPA secure basically. Ma'am, can you please repeat 2-3 point of 3 question due to my what do you mean the part 3 I have not touched yet. First part is clear, Kapil. First part is clear, right? The second part I am discussing. So for second part, just observe that fk0 to the power n, this is a pseudo-random string. So if you are XORing your plain text with a pseudo-random string, okay, then it is secure in presence of eavesdropper. Just like your OTP scheme. In OTP scheme, what do? You are in OTP, which is perfectly secure. In fact, you are XORing your message with a truly random string. The key, right, which is truly random of same length as of the plain text. Okay, but here it is not truly random, but it is a pseudo random string, and with that we our target is accomplished, right? It is a pseudo random string, so it is indistinguishable from a truly random string except with negligible probability. So you are XORing your plain text with a pseudo random string. Why it is pseudo random? Although you know the plain text is always zero, although you know the input of PRF is always 0 to the power n, but you don't know the key. Key is secret in view of adversary. That is why the output of the PRF on a known input with the unknown secret is pseudo-random. So M XORed with fk 0 to the power n is does hide the underlying information about the message M. So it is secure in presence of eavesdropper. That is the first case, but it is not CPA secure. Why? Because this is a deterministic encryption scheme, and we already discussed that a deterministic encryption scheme, which is also stateless, is never CPA secure. So CPA security is not maintained here. Now coming to the third part. So hope that is clear, Kapil. The second question is clear. Okay, thank you. So now coming to the third part. Anyone would like to answer what is this third part? Is it secure in presence of eavesdropper and is so first tell me about eavesdropper scenario. So what is being done? Your message is now 2n bit length, okay, and you are taking it as 2n bit length. So your M has total length 2n. You are observing this such that it is concatenation of 2n bit length message. Now for encryption, you first choose a uniform random R, a random string, and then you encrypt the first part by XORing the first part with fk of R, and then the second part is by XORing it with fk of R plus 1. This is your final ciphertext. So in the ciphertext, you are able to see R. F is a public algorithm, the PRF algorithm, but K is hidden. K is not known. So FKR is a pseudo-random string. FKR plus 1 is another pseudo-random string. And there is no relation between FKR and FKR plus 1. Why? Because although R and R plus 1 are related inputs, but because we apply the function, pseudo-random function F in both the cases, the outputs are not correlated. So they are indistinguishable from a truly random string. So FKR and FKR plus 1 are completely pseudo-random string. So your M1 and M2 are getting XORed with two different pseudo-random string. Okay. And knowledge of R also does not leak anything about FK of R. Why? Because K is secret. Now, is this secure in presence of eavesdropper?
Yes, ma'am.
It will be secure, right? So it will be secure. Clearly. Now, what about the CPA security? Is it CPA secure as well? That is, by querying it multiple times, will it help in distinguishing the encryption of M0 from encryption of M1. Again, here M0, M1 will mean that M0 is also a 2N
Yes,
bit length string, like this. M1 is
ma'am,
also
on every query, we will get a random R.
correct.
So function will output a random value, then it will be CPA secure.
Right, it will be CPA secure because it is now a randomized encryption scheme. It is not anymore deterministic. And also you can show formally that assuming there is an adversary who is able to distinguish the encryption of some M0 of this form from encryption of M1 with non-negligible probability will imply existence of another adversary who is able to break the security game of PRF-F. Okay, that can be used to prove by contradiction, okay, that it is CPA secure. So you can see here the game is written. So again, there is this challenger or verifier who is playing the PRF game with this adversary A. And there is another adversary A dash who is playing the CPA security game of the encryption scheme. So the game starts with this, that the verifier or challenger first decide whether to send out PRF output or truly random output for some query input. And also here what happens in this part, so A dash as an adversary for CPA security game will send messages of its choice. So some query message MI will be sent to A, and what A does, A actually samples some random value Ri, and for that corresponding PRF evaluation, that Fk of Ri is returned back. Or rather, I should say Yi. Yi can have the form of PRF or truly random function. So Yi will be sent back to A. And similarly, for input Ri plus 1 also, A will get to see the output Yi dash, which is again either PRF evaluation on Ri plus 1 or truly random function evaluation on Ri plus 1. Now, once A gets both Yi and Yi dash, it will use them. Oh, sorry. It will use them to find the ciphertext that is of the form Ri, comma, Mi1, that is the first n-bit part of the message Mi, XORed with Yi, and the second part Mi2 XORed with Yi dash. That is the ciphertext corresponding to Mi in the view of the adversary A dash, who is playing the CPA security game with A. Now, this query phase can continue for polynomial number of times. Now, in the challenge phase, the adversary A dash will send two messages of its choice, M0, M1, and then A will again choose some R uniformly randomly, right? And then both R and R plus 1 will be sent to verifier, and their corresponding PRF or TRF evaluation will be sent back to A in form of Y and Y dash. So Y is evaluation on input R, Y dash is evaluation on R plus 1. And then using Y and Y dash, and also A chooses a bit B dash, right, to decide whether to encrypt M0 and M1. That is the standard CPA security game, like that it goes on. So either M0 will be encrypted or M1 will be encrypted. Accordingly, let's say the bit B dash has been chosen. So MB dash, that first part of MB dash, denoted as MB dash 1, is XORed with Y. That is the evaluation of PRF-F on the input R. And the second part of message MB dash, denoted with MB dash 2, is XORed with Y dash, which is the evaluation of PRF-F on input R plus 1. So the way this our encryption scheme is defined, that is the way this ciphertext is built and sent to adversary A dash. Now, if we assume that A dash is able to guess the bit B dash with non-negligible probability, that is, A dash is able to break the CPA security of this game going on between A and A dash, then if A observes that A dash has guessed the bit correctly, then it will send B equal to 0. That is, it will declare that, okay, I was interacting with a pseudo-random function f. And if A dash is unable to guess the bit B dash correctly, then A will declare that I was interacting with a truly random function. Okay. Now see, if indeed verifier chose to send FK, that is the PRF output for each of these query input, then in the view of the adversary A dash, it was actually playing the game for CPA security of this defined encryption scheme. And if the response YIs are actually truly random string, then in the view of adversary, it is they are some random encryption scheme, right? It is not the defined one that we have seen. So the way if A dash is able to distinguish between these two cases, then A will also be able to distinguish between the truly random output and pseudo-random output, or PRF and TRF values. So that is how we say that the scheme is CPA secure. Okay, there is some question. Vanita is asking, ma'am, exam will be descriptive or objective type question? I think both type of questions are there, but I'm not sure actually. Okay, your assignment questions are objective. See, that really does not matter. Okay, if you understand the concept, I mean, if you even have seen the assignment questions that are posted in NPTEL website, although they are in form of objective question, but in most of the cases you have to get pen and paper and try to find out what is happening. That is a descriptive way. It's not like some you just read the option and you know that whether it is correct or not. You have to give it a thought, right, to consider with what is going on. So although questions are in objective form, your thought process has to be descriptive. And if your thought process is correct, you can just put it on paper also, right? Or write it on the computer screen. But I will let you know in the next class, okay, that whether it will be descriptive or objective. I will try to find out from someone. I am not sure. Okay, thank you, Vanita. So is this question or is this discussion answers your question? This third question? Any confusion? Okay, I hope this is clear. So let me proceed to the next question. So here is another question. What is the effect of a dropped ciphertext block? Example, if the transmitted ciphertext C1, C2, C3 is received as C1, C3. So C2 is dropped when using CBC, WebB, and CTR modes of operation. So they are like modes of block cipher. Okay. So I think let me just recap once what are the CBC, WebB, and CTR mode of operation. So what happens in CBC, that is the cipher blockchaining mode of block cipher, right? So here you use some pseudo-random function fk, right? And your this is the modes of block cipher operation, right? So your message actually is divided into multiple blocks of some particular block length, right? So they are your message. And in CBC mode, you first choose some initialization vector IV, and then you pass M1 XOR with IV to FK to generate C1, and then C1 is passed to the next state. M2 is XORed with C1, fed to the pseudo-random function. K is secret, of course, and like that it goes on, right? So this is how CBC mode of operation works. So on. What about OFB? So this is CBC mode. Output feedback. So here what happens? You again have this pseudo-random function block. Now in OFB, basically you directly pass the initialization vector, and with the output of this, your message is actually XORed with, and you get C1. And from this part, like this, right? This is M2, C2, right? And so on. Ma'am, can you explain CBC one more time? Okay, Viresh. So CBC explain means, I mean, now we are dealing with a single message which is quite long, right? So your plain text is now of this form, divided in blocks of same size. Okay. Each block you name as M1, M2, M3. And at a time you want to encrypt M. So you divide M in multiple blocks of same size. Let's say N. Each of the block has size N bit. Now M is, so M1, M2, M3, all of the blocks are uh, encrypted in this manner. So you first choose a initialization vector. Okay. Let's say of this space uniformly randomly. So this is a uniform random string IV initialization vector. And now your message is first XORed with a random string, right? So then fed into this pseudo-random function, and the output of pseudo-random function is denoted as C1. That is the encryption corresponding to message block M1. So your final cipher text in this case becomes IV, C1, C2, C3, because there are 3 blocks in the messages. If there would have been more blocks in the message, then you could have continue C4, C5 like this. So assuming your message has 3 blocks, M1, M2, M3, your cipher text will have this form: IV, C1, C2, C3. And how you decrypt? For decryption, you take each CI. So I can write that MI is nothing but FK inverse of CI XORed with CI minus 1. Sorry. CI minus 1 in the subscript, right? What does it mean? Like, to retrieve back M1, you do FK inverse of CI, that is C1. You get back this value, and with that you XOR IV. IV is considered as C0 here. Okay. If you look at C2, you perform FK inverse C2 to get back the value at this point, and you XOR it with C1, that is CI minus 1, and you get back M2. Like that, you decrypt. So this is your decryption strategy. So this is how the encryption scheme is defined. Is this clear, Viresh?
Yes, ma'am. Yes, ma'am, it is clear.
Okay. Now in output feedback mode, you don't do the XOR operation in the beginning. You first apply the function, pseudo-random function, and then do the XORing with the message. Okay. Now here also against the ciphertext has this form: IV, C1, C2, C3. All of this is the part of the ciphertext. And for decryption, what you do? MI is CI XORed with FK of CI minus 1, right? Correct. So to retrieve back M1, you compute FK of C0, that is IV, and XOR it with C1. So you get back M1. So here actually, if you notice, inverse function is required. So in this case, F has to be a PRP. Okay. F being PRF is not enough, because invert function has to be defined on F. Otherwise, you cannot compute this unambiguously. But here, You can use any pseudorandom function. It is not necessary for it to be a pseudorandom permutation, or because invert function is not necessary for decrypting purpose. So MI is computed in this way. Is this clear? This is the output feedback mode of block cipher. One thing you can notice that in CBC mode, you cannot compute the value of, let's say, MI unless you know the value of Ci minus 1, right? To decrypt the value of Mi, you have to have the knowledge of Ci minus 1. And so basically this is sequential. What I mean to say is that only when you know the value of M1, you can compute the value here, right? The output value of the PRF can be computed. So let's forget about decryption. In encryption process also, once you don't know the value of C1, you cannot compute the value of C2. If you don't know the value of C2, you cannot compute the value of C3. So it goes on sequentially. First you compute the value of C1, then you compute the value of C2, then you compute the value of C3. But in case of wave B, you actually your C1, C2 needs the okay, again I should repeat that once this message ends in 10 minutes, you can join back in the same Zoom link. Okay, let's continue. So although C1 needs the XORing of M1, but before that, at this point of value, if we denote this value as Y1, this point value is Y2 before XORing with Mi. Okay, so these values can be pre-computed actually. All the YI values at this point, this point, this point can be pre-computed before you know what exact the message is. In this case, to compute the value of C1, you have to know the value of message M1. So until the point when you get to know what your plaintext message is, you don't know the value of the output of pseudorandom function. But here, even you don't know till this point that what is the message that you have to encrypt, but you can pre-compute this value of yi. How you can compute fk of yi minus 1, and that does not depend on the plain text. So all the yi values can be pre-computed, and after you see the messages, you can just XOR them with so your ci is nothing but yi XORed with mi. So after you see the message, you just get the XOR operation done on all of the blocks, and you get to compute the value of the ciphertext. That is one advantage of OFB mode over CBC mode. Anyway, for CTR mode, counter mode, here again you have these boxes for pseudorandom function. This is similar to OFB with only difference is that here instead of initialization vector, we name it as CTR, the first value that is fed into the pseudorandom function box, and then this is XORed with M1 to produce C1, but there is no dependency from here to here. What you provide here is CTR plus 1. So nothing to do with this evaluation value of FK. You just put here CTR was provided, here CTR plus 1 is provided, or maybe you can think of just to maintain the consistency, I can also write that CTR is provided as C0. The first block is CTR plus 1 provided to the function fk, XORed with M1 and produces ciphertext C1. Here CTR plus 2 is provided, and this CTR plus 3 is provided, and then XORed with M3 produces C3. So ciphertext still has the form CTR, C1, C2, C3, and your decryption is MI, is retrieved back as Ci XORed with Fk of CTR plus I. Now notice here, even before you know the value of the message, you just know the value of counter and you can parallelly compute all the PRF values here. All this value here still yi is dependent upon the value of yi minus 1. But that dependency is also removed in this case, right? Here all the value here, if I denote this y1, y2, y3, all of them can be parallelly computed because you know the value of CTR. You parallelly feed the values of CTR plus 1, CTR plus 2, CTR plus 3, all of this parallelly, and then exert them with MIs to produce the CIs. Okay, so this is parallelizable, the CTR mode. In the chat, ma'am, is IV chosen at random or is it a definite value? It can be chosen as random, no problem with that, but because it is already being provided as the ciphertext, right? It is not as fixed value because otherwise it will be a deterministic scheme, right? Key is fixed, right? And if you fix the IV as well, so every time your this thing will not anymore be deterministic, right? So IV is random, but still IV is being provided as part of the ciphertext. So IV is a known value. By seeing the ciphertext, you know what the value of IV is, but this is not fixed. Okay.
Okay, ma'am.
So these are the three modes. I just wanted to recapitulate. Now coming back to the question, exactly what happens here. So the question is saying that what happens if the transmitted ciphertext drops a particular block. So let's say, for example, as I said that I am supposed to receive IV, C1, C2, C3 as the ciphertext. But what if I receive IV, C1, then C2 is dropped, right? So let me write. Okay, let me explain from this figure. That is better. So this is, we are taking 4 blocks of message. Okay. Now C2 is dropped. So what I receive is this C1, C3, C4 and C5. I was supposed to receive IV, C1, C2, C3, C4, but I received IV, C1, C3, C4, C5, which is there somewhere. It is continued. Okay. Now, in CBC mode, this is how CBC mode works, right? So what happens with decryption of M1? So this is decrypted correctly because nothing has been changed here. Okay, M1 is correctly decrypted. What about M2? So C2 was dropped. So as per the decryption algorithm, what I do FK inverse on the second ciphertext, which is C3 now. So FK inverse C3 XORed with Ci minus 1, that is C1 here, because I received C1, then I received C3. So with respect to C3, this C1 is the Ci minus 1 in the view of the receiver of the ciphertext. So Fk inverse C3 XORed with C1 is performed. But this Fk inverse of C3 does not give the required value of M2 because M2 would have been produced if I had done Fk inverse of C2 XORed with C1. But that is not the case here, right? This value is nothing but C2 XORed with M2 here, right? The input to this Fk, if I compute Fk inverse C3, that will give you M3 C2. So C3 is here, right? Fk inverse of C3 is this value, which is M3 XORed with C2. And that is XORed with C1. So this is clearly not the value of M2, right? So this is wrongly retrieved. The second plaintext block. What about the third plaintext block? So what I do Fk inverse C4 because as the third ciphertext block I received C4. So I do Fk inverse of C4, which is M4 XORed with C3. The value of Fk inverse of C4 is actually M4 XORed with C3. And now the result is XORed with C3. according to the decryption algorithm, because that is Ci minus 1 as received with respect to C4. Now you get back M4. So I was supposed to get M3 as the third plaintext block retrieved, but I received M4. So this I can say that it is shifted by one position. The decrypted plaintext in the same manner, if I see, M1 has been retrieved, M2 could not be retrieved, even M3 could not be retrieved, but as I received M4, M5. So in place of M3, I actually get to see value of M4. In place of M4, I get to see the value of M5. So it is shifted by one position, but the value of M2 and M3 are completely lost, right? So the Zoom meeting is less than 1 minute left. So after that, it ends and you join back in the same link. Now this is about CBC mode. And what about WebB mode? If you just look at this, so the way WebB mode decryption is defined, I said MI is CI XORed with YI. This is the value of YI at this point. So M1 is correctly retrieved, no problem with that. But in place of C2, I received C3. So I do C3 XORed with Y2. That does not give at all the correct value of M2, right? And so once ith block is dropped, after that, all the blocks are not retrieved correctly. So once CI is dropped, I minus 1 messages are decrypted correctly before that. So like M1 is decrypted correctly here, but after that, every recovered blocks are wrong. So now for the counter mode, actually, the just like the WebB mode, the situation will be there in counter mode as well, because in counter mode also, if you drop the ciphertext, okay, let's say C2 has been dropped. So what you receive is CTR, C1, C3, C4 like that. So here also your M1 will be retrieved correctly because this is C1 XORed with FK of CTR plus 1. So nothing has changed here. M1 will be retrieved correctly. But then for M2, what happens is that you will do C3 XORed with FK of CTR plus 2 because you receive C3 in place of C2. So that is why your M2 will not be actually correctly computed. So you can't retrieve M3 and so on. For all the rest of the messages, you will not get the correct answer because this part is fixed for ith block for any MI, but CI has been changed. So you cannot retrieve back MI actually. So this is the same for as of WebB scenario. So proceeding to the next question. Which of the following is or are false about modes of operation? A sequence of n messages can be encrypted using block cipher by making less than n calls to a secured PRF. So is it true or false? Anyone? So n messages you can think of like n message block, right? As I said in the previous slide that M has 3 parts, M1, M2, M3. So if M has n parts, n message block, can they be encrypted using less than n calls to a secure PRF? It's not true actually, because as we had already seen for all the modes of operation, if we have M1, M2, M3, then we need to use 3 blocks of pseudo-random function to get C1, C2, C3 along with the initialization vector as C0. So this is not true. Ciphertext computation is parallelizable in CTR mode. So this is true or false? Just now I discussed in the previous slide actually.
It is true, ma'am.
It's true, right? Because you can compute all the previous values parallelly, y1, y2 to y3, I just said. Plaintext of any length can be encrypted in WebB mode. So is it true? This was also I mentioning, so referring back to this figure, so it was WebB mode, right? So in WebB mode, just observe that even if you don't know what the message is going to be, you can compute all the YIs accordingly, right? Then even if you don't know the message length, let's say your last block of message does not have the bit length of n, assuming that all the y1, y2, y3, all of them has bit length of n, but your last message block mi happens to be a lesser than n bit length, then what you can simply do, you can just use first n dash. So if mi has length n dash less than n, you just use the first n dash bits of the yi to XOR with the last block of message. So the message length does not matter. Whatever your message length is, your m can have this form, m1 concatenated with m2 till ml, and ml may not have length n, but still that is not a problem for OFB mode. Even for CTR mode also that is not a problem, because your you can compute the yi's just pre-compute, you can all the yi's and just use first n dash number of bits accordingly, whatever is the length of ml. So you don't need to use the whole yi. But in CBC mode, you need to know the message length, and also if it is not multiple of the block length, then you need to do padding and all. So you will see that also. So this option is correct, that plaintext message of any length can be encrypted in OFB mode. It does not need to be multiple of the block length. Okay. Stateful variant of counter mode is secure, whereas that of OFB mode is insecure. So stateful variant means that, as I had seen in, so for let's say OFB mode, you have this y1, y2, y3 here, and you exert them with m1, m2, m3, right? All these are passed. There comes IV, and you get the ciphertext. So let's say your first message had two blocks, m1, m2. Then you are going to encrypt another message coming separately, which again has two blocks, let's say m1 dash, m2 dash. And for that, your initialization vector, instead of using some other IV dash, instead of using that, if you use this y3 only as input here, and then doing the rest of the operations as it is. Okay. What happens with that? So does it raise any new problem or not? So basically, this will not be a problem in case of OFB, output feedback mode. Why? Because your FK evaluation is going on this y3. So even if you know the value of y3, you can't guess the value of fk of y3, because f is a pseudo-random function and key is secret. So this value is still pseudo-random, and you are XORing your m1 dash with a pseudo-random value. And same is applied for counter mode as well. They are also stateful version is this only. So once your first message, let's say m0 is m1, m2, and your next message, separate message is m1 dash, m2 dash, and you are using the, instead of using some other initialization vector, you are using y3 only here as the input to PRF. That is the stateful version. In counter mode also, stateful version does not raise any security concern like the OFB mode only, because your pseudo-random function is applied on the version that you were passing through from previous encryption result. But in case of CBC mode, this is not secure, the stateful version, because in CBC mode, if you see what happens, you are XORing it fast with the message block, right? And then applying this to get C1, and like this you pass, right? So let's say your first message is m1, m2, and then when you are encrypting m1 dash, instead of using some other IV value, if you use C2 only, right? And then continue doing that. m-2. Here what can happen is that your C2 is already known, right? And you are directly XORing m1 dash with this known C2 value. Here XORing the message with a pseudo random value because fk has already been applied on y3. But here you are XORing m1 dash with known C2 value and then passing it to fk. So that actually raises a concern. We can show. So I will show in. So let me proceed here. Right. So here okay, there is in chat. Ma'am, could you repeat the stateful part once? Stateful means that we are somehow using the previous state in encryption of next message. So if it is independent of the previous, so your CPA security game goes on like this, right? MI, you get to see CI. Then you send some MI plus 1, some other message, and you get to see CI plus 1. Now, this computation of CI plus 1, if it involves some knowledge from the computation of CI, then it is stateful. But if it is completely independent of this computation process of previous message value or previous encryption, then it is stateless. Here, why is it stateful? Because in computation of encryption of MI plus 1, you are using this Y3 value, which was the part of previous encryption of M1, M2. That was a separate message. Now, for another message, M1 dash M2 dash, which is completely different from M1, M2, instead of using another initialization vector IV, you are using knowledge of Y3 from the previous computation process and making that use in the computation of CI plus 1. That is how your state is preserved. You are preserving the state from the previous encryption and using it to do the encryption of next message. That is why it is stateful. Am I clear?
Yes, ma'am.
Where can I access the material? Okay, this will be converted to YouTube video, and that link has already been shared with you. I think you were registered in the NPTEL website, right? So where you see the assignments and all, there only you will find a link to an Excel sheet where all the YouTube link will be given under the heading of problem solving session recordings. There will be some tab. Okay, there you can find all the YouTube videos for each. Okay. So coming back to this part, that counter mode of OFB is secure. I said, stateful variant of OFB mode is secure. Stateful variant of CTR mode is also secure. So this statement is of course false, the last one. But stateful variant of CBC mode is not secure. How? Because here you see that let's say, first assume a challenge phase, right? So in challenge phase, the attacker gives two plain text, M0 and M1. M0 has this form, two part, M01, M02, and M1 has again two part, like two blocks. Okay, so this is your M0, this is your M1. Now your challenge ciphertext has this form, IB, C1, C2. This encrypts either this or this. Now, how the attacker can know what exactly has been encrypted under this challenge ciphertext? So it will, in the post-challenge query phase, after seeing the challenge ciphertext, it can query the challenger with a specially crafted message of this form. So maybe it is querying with some other message that has two blocks, M3, M4, such that the first block, M3, has this particular form, which is C2 XORed with IV, XORed with M10. M10 is known because it was chosen by adversary only. IV is also known because it is given in the challenge ciphertext. C2 is also known. It is given in the challenge ciphertext. So all the informations are known, and M3 has been created like this, and then it is querying the challenger with the message block M3. Then what happens is that when encrypting, how C3 will be computed, corresponding ciphertext for M3. So C3 will be computed like this, Fk of C2 XORed with M3. Why? Because as I said that previous state C2 is being used in the stateful variant of CBC mode. So for a new message M3, C2 has been used. C2 was part of the previous computation. So Fk of C2 XORed with M3 gives back C3. Now M3 has this particular form, C2 XOR IV XOR M10. So this C2 gets cancelled and what I get is Fk of IV XOR with M10. Note that C1 is nothing but IV comma M10 if the underlying message was M10, right? So by matching whether this C3 is equal to C1 or not, if it is equal to C1, then I say that underlying message that was encrypted was this. Otherwise, I say the encrypted message is this. So I can distinguish whether I am seeing encryption of the first message or the encryption of second message. That's how CPA security is broken in stateful variant of CBC mode. So I hope that is clear. Okay. Now coming to the next question. Consider the stateless variant of CBC mode of encryption with a block cipher having a 256-bit key and 128-bit block length to encrypt a 512-bit message. The length of the resulting ciphertext bit. So just now I mentioned that in the CBC mode, I need to know the message previous, like first I need to know what the message is and then I can perform the encryption, which is not the case of OFB mode and CTR mode, because there I can compute the value Y1, Y2 and all previously, even before I see the message. But that is not the case of CBC mode. I already mentioned. Why is that? Because there may be the case that M1 is concatenation of M2, M1, I mean the message M is concatenation of M1, which has block length N. This is also N bit. And let's say M3 has a lesser number of bits to it. Okay, let's say N dash, which is less than N. So I need to basically pad this last message block M3 so that it becomes the of the same length as N. So I have to make this N dash bit padded with, such that it becomes N bit, so that a complete block is there. So for padding, what strategy we take is that we basically append. So rather than bit, let me tell byte. So let me tell that M1 is N byte, M2 has length N byte, and M3 has length N dash byte, such that N dash is less than N. So I need to append N minus N dash number of padded byte, such that each byte, so the bytes you pad, this is the actual content of M3 and this is the padding you do. Each byte you add, so let's say they are total N minus N dash byte of padding. Padding is some extra bit which does not contain information about message but does contain information about the length of the message. So each of these N minus N dash byte contains the value N minus N dash. So what I mean to say is that let's say your M1, M2 all has byte length of 16, let's say. Now M3 has byte length of 7 initially. So I need to append 9 more byte to it, and each of these byte will contain the value 9. That is 1001, right? This is the value 9 in binary. So byte means 4 bits, 8 bits are there. So 00001001. This will be the content of each of the extra byte that you pad. So there are total 9 padding byte will be there, and each of them 1, 2, 3, 4, 5, 6, 7, 8, 9, and each of them has the content this. So what does it mean? So you try to see the last. So when you perform FK inverse of C3, the last byte, and then XOR it with the value of C2, what you get? You get M3. Now you see the last byte value of M3, that is 9 in this case. And then you know that last 9 bytes are actually padding bytes. So you discard those 9 bytes, and then you know the rest of the part actually are the original message contents. That's how the padding is done in CBC mode. Now the question says that your block length is 128 bit, that is 16 byte again, because 1 byte is 8 bit. So 16 byte block length are there, and you have 512 bit message. So this is actually multiple of 128 bit, right? So 4 blocks of original message are there, M1, M2, M3, M4. But still we need we have the need to padding. Okay, so I will actually provide another block M5 such that the whole of it actually contains the padded byte. So it also has total 16 byte. So 16 byte will be there in M5, and each of the bytes will contain the value 16 there. Okay, so that is 000100000. This will be the content of each of the 16 byte of the message block M5, to denote that whenever you read the last byte of block M5, you know the value is 16, so you discard 16 bytes there and you take the original message value this. So how many length of resulting ciphertext? So ciphertext has this form, right? IV, comma, C1, C2, C3, C4, C5. And so how many are there? There are total 6 blocks, and each has 128 bit length, right? So, okay, just one thing I think I missed is that okay, so 1, 2, 3, 4, there are 5. Did I miss something? Resulting ciphertext actually should also contain the value of IV as well. So in that case, I think this should be 6 into 128, but this has been worked out as 5 into 128 bit. Okay, I think I will check this once again. Okay. Now coming to the next question. Fk is given as a secure PRF. Define Fk dash. If x is even, then you provide the value of f of x. Okay. So you can consider the k is here also. Okay. Fk of x and Fk of x plus 1. This is how another function f dash is defined. And you have to say whether f dash is secured PRF or not. So anyone would like to comment on the security of f dash, the way it is defined? X is even means the last bit of x is 0. X is odd means last bit of x is 1. Can you exploit this particular pattern of evaluating PRF to attack the security of f dash?
Yes, ma'am.
Okay.
If we see that there's an input that has a 0 at the last, and we get an output,
Right.
and we increase the input by 1, and then we get a different output, but then we increase that by 1 again, and we again get 0 at the end. So get the same output.
Right. Your direction is correct. So what you can do is that you query with, so let me come here. So you first query with x1 of this form, right? The last bit is 0, and you get back y1. right? So since this is 0, this is even. So y1, if it is a PRF, then y1 has exactly the same form as fk of x1. Now you change like query with another input which has this form. Okay, first n minus 2 bits are 1, then 0, then 1. Now since this is a odd number, if you add so all ones 0 1, if you add 1 to it, what happens? This. So your resulting string is 1 n minus 1 0, right? This is the same as x1. So for x2, it will again actually give back this, because x2 plus 1 is x1, right? So you know the value, if you are interacting with the pseudo-random thing, you are getting the value of fk of x1. And here also, for querying with this odd input, you are getting the value of fk of x2 plus 1, which is nothing but fk of x1. So these two value will be same. So if you are indeed interacting with a PRF, this strategy of adversary will work with probability 1. But if you are working with interacting with a truly random function, then probability that two n-bit length string are same, that happens with 1 by 2 to the power n probability. So the distinguishing advantage of this adversary is 1 minus 1 to the power n, which is not negligible. So the security of the PRF is broken by this adversary. So this is not a secure PRF. Okay. So this question, let F be a secure PRF. So n-bit input, n-bit key, and n-bit output. Which of the following constructions is or are not necessarily a secure PRF? Let's take one after another. The first one. Any comment on this? Okay, let me rather tell that this is not secure. Now how we will attack? What will
If
be your
we
yes?
if we give the input as all the bits as 0, then by XORing we will get output as 0. So it can be distinguished from a truly random function.
Right, right. Even so, yes, your answer is correct. So let's say your input is of this form. So what you get? You get fk of 0 to the power n XOR with fk of 0 to the power n, which is nothing but all 0. I mean, all 0, right? Also, like any repeated string you send, so you send x1 in this form. So first half of the input and second half of the input are same for your query input. Then whatever you get, it is all 0 string, right? Even another strategy could be, so this is done with single query. But if we allow two queries, then also you can just first query you give some random string of form x comma y. In the second query you give this. Then also you will see the same output in the two cases, right? That will also work. Like in various means you can attack the system. What about the second one?
It will also not be secure, ma'am.
Also not secure. Very clearly, like if you are understanding the first one, second one is also similarly done. You just maybe send this and you get to see same first half and second half in the output stream, and you are done. Okay, not with non-negligible probability, which you can distinguish. What about the third one? This is bitwise AND.
Yes, ma'am, it is not secure because if we give one input as all ones and other input as all 0, then we can notice that the bitwise AND is coming out to be 0. So it can be distinguished from an output of a truly random function.
Wait, you were saying that you will first give all 0 and this will give you fk 0 to the power n XOR with fk 0 to the power n. That is what you were saying. Is this
No, ma'am.
what
I
you
was
said?
saying if I will give ma'am x is equal to all 0 and y is equal to all 1. But I think, ma'am, we can't this thing give a separately input x and y.
Right, so this may not work because that will give you this, but seeing the output on this input you cannot distinguish because this will be pseudo random. But what you can do is that first you give this as the input, then you give this as the input. In both the cases, if you will get the same result, right? Fk of x ANDed with Fk of y. Here you will get Fk of y and with Fk of x, and they are same. And you are done with that again, right? This
Yes,
strategy
ma'am.
will work.
Yes.
Yeah. And the last one, x XORed with 1 to the power n is nothing but x bar, complement of x. So how will you attack the system? This is also not secure, clearly. What will
And
you
if
do?
we give x is equal to all 0, then we will get the same uh, strings of input at both ends.
If you get all 0,
X is all 0. Yes,
hmm,
and then
then I get,
both strings after concatenated.
and next you get 1 to the power n, then you get this. Yes, that will work. That will work. In fact, it is correct. In fact, you can give as input any x and see the see the output, and then provide x bar and see the output. And it will always be the case that first half of second output is exactly equal to the second half of first output, and first half of first output will be exactly equal to the second half of second output for any x and x bar as input. So 0 to the power n, 1 to the power n is a special case of that. For any x and x bar, this will work, right? So,
Yes,
thank
sir.
you. Nice answers from your side. Uh, Here is another question. I think there are only 7 minutes are left. So let's wrap up quickly. What it does is that let F be a pseudorandom permutation. Consider mode of operation in which uniform value CTR is chosen and the ith ciphertext block CI is computed as CI equal to FK CTR plus I plus MI. So that is how each CI block is defined or computed, so that the scheme does not have indistinguishable encryption in presence of eavesdropper. I think let me just discuss this quickly. So there is no query phase because we are considering just the eavesdropper security. So no query phase is there. Just directly there is two messages chosen by the adversary, M0 and M1. You can craft the M0 and M1 in this way that M0 has the encoding of 1, the number 1, followed by or concatenated with the encoding of 0. Okay. And M1 has this form 0 concatenated with encoding of 1. So this angle bracket just means encoding of 1. Like if I write 1, this is a number 1. But if I represent 1 as, let's say, with sufficient padding and all as a particular bit length of block, that is encoding of 1. Okay. Same for 0. Now, what happens? CB is returned for encryption of MB, and CB has this form, right? So if B is 0, that is M0 has been chosen to be encrypted, then your CB has this form. Fk of CTR plus 0, this is the I. Since this is 0th block, so 0 is encoded plus Mi is 1 because first block of M0 was 1. And the second block, which is 0, Fk of CTR plus 1, because this is the 1, this is 0th block, this is 1th block, so this is the value of I plus the Mi, so Mi is 0 here. So you get basically, see the input to the Fk is same. So you get ciphertext of this form CTR, C, C. But if M1 is selected to be encrypted by the verifier, then your the two inputs to Fk is different, so you get two different ciphertext, right? So observing the pattern of the ciphertext CB, whether the last two parts are exactly equal to each other or not, you can determine whether M0 was selected or M1 was selected as the underlying message for challenge ciphertext CB. So this is not secure in presence of a eavesdropper. Is this clear?
Yes, ma'am.
Okay. Stateful variant of CBC mode encryption where the sender simply increments IV by 1. Okay. So this is also, I already discussed why stateful variant of CBC mode is not secure, right? So there I had shown that for two message blocks, so for the first message you get IV comma C1 comma C2 for a message corresponding to M1 M2, and then for another message M3 M4 you are crafting M3 in this form that it has this C2 already known, XORed with IV, XORed with M1, right? And then when you are trying to encrypt M3, then what you do M3 XORed with C2, right? Now, because of the way M3 is crafted, the C2 gets cancelled and your FK IV XOR with M1 is received, with which you compare whether it is equal to C1 or not. So this is the similar question, only with the only difference is that instead of C2, you are using IV plus 1 to the first FK box. So instead of C2, you just put here IV plus 1, and then the rest of the scheme is same. Ma'am, could you please repeat why stateful variant of OFB and CTR is secure? Okay, so the main reason being that because, here before feeding the value to FK box, the pseudorandom function box, you are XORing, right? But in case of CTR and OFB mode, the input to FK are unaffected, right? The XORing happens later. So you pass for stateful variant, you receive IV comma C1 C2 here also, but you use instead of C2, the way your stateful version is defined is that this part goes to the next output, next input to FK, right? So it is not C2 what is actually used in the encryption of M3. It is actually Y2 that is fed into FK, and then your M3 gets XORed with this. So intuitively, your FK part, the input to pseudorandom does not get affected with the way your message M3 is designed. So here you can design your query message in such a manner such that you make the encryption oracle output a ciphertext with which you can compare your challenge ciphertext. But here you cannot do anything with the design of message M3 because M3 does not affect the evaluation of pseudorandom function. M3 is XORed later, right? So you cannot do anything like the way you did here. You designed M3 in a way such that you get to know what the underlying plain text is in the challenge ciphertext. But here you cannot do the same strategy. If you are able to break the CPA security in stateful version of OFB mode, that will imply that you are able to break the security of the PRFF. Okay. Is the intuition clear? You can find the
Yes, ma'am.
formal proof in the book maybe. And we have actually less than 1 minute left. So I think let me stop here. And thank you for participating. Okay.
Thank you very much, ma'am.
Yeah. Thank you. So I will end the meeting now. And next week we will discuss the assignment questions for week 4. Okay. And then that we'll discuss questions from the topic of week 5. Okay. Yes. Thank you.